I'm Mrita from Institute of Aeronautical Engineering, Department of Electronics and Communication Engineering. My Tech Talk topic for VLSI design is FPGA architecture, principles and progression. Introduction to FPGA architecture. Field Programmable Gate Arrays is the abbreviation of FPGA. FPGAs are integrated circuits that can be configured after manufacturing. They provide customizable hardware solutions for a wide range of applications. Understanding their architecture is essential for optimizing performance and flexibility. Historical background and evaluation. FPGAs originated in the 1980s as a reconfigurable alternative to ASICs. So, over time, their complexity and capabilities have significantly increased. Progression reflects advances in semiconductor technology and design methodologies. Basic FPGA architecture overview. FPGAs consist of configurable logic blocks, CLBs, input output blocks, and interconnects. CLBs contain lookup tables, means LUTs, flip flops, and multiplexers for logic functions. Interconnects provide programmable routing among the logic blocks and input output IO blocks. So here we can see the FPGA architecture overview where CLBs contain lookup tables, LUTs and multiplexes for logic functions, and here in middle we can see the interconnects provide programmable routing among the logic block functions. This is the FPGA architecture overview. Configurable logic blocks. CLBs are the fundamental units where logic functions are implemented. They typically include LUTs for combinational logic and flip-flops for sequential logics. So LUTs are lookup tables. So where lookup tables are used for combinational logic and flip-flops are used for sequential logic. The flexibility of CLBs allows for a wide variety of digital functions. Lookup tables in CLBs. Lookup tables are very small memory structures that implement any Boolean function of inputs. They enable fast and flexible logic implementation within the FPGA. The size of LUTs has increased over time, enhancing the FPGA's computational capacity. So the size of lookup tables will be increased over time, enhancing the FPGA's capacity. So here we can see the here the lookup tables in CLBs we can see the n input lookup table LUT to flip flop. So that implements any LUTs has increased function based stored using the truth table. So they enable fast or flexible logic implementation within the FPGA. Interconnect architecture. Interconnects are programmable routing resources that connect CLBs and IO blocks. They consist of configurable switches and wiring to facilitate flexible circuit design. The density and richness of interconnects directly influence FPGA performance. IO blocks and their role. IO blocks manage the communication between the FPGA and external devices. They support various standards and voltage levels for interface compatibility. IO configurations are programmable to suit diverse application requirements. So here we can see the IO blocks which are connected to the FPGA core fabric, CLBs and interconnects. On the left side we can see the external connections, DDR memory and GPIO header. On the right side we can see the USB connector, etheractor, voltage, protocol support and all. So these are the role of the IO blocks. Memory resources within FPGAs. Modern FPGAs incorporate embedded memory blocks like block RAM. These memory modules support storage buffering and FIFO functions, where FIFO abbreviation is first in first out. Embedded memory enhances the FPGA's ability to handle complex data processing tasks. DSP and specialized processing elements. DSP abbreviation is digital signal processing. So, digital signal processing slices are dedicated blocks for arithmetic operations. They accelerate computation intensive tasks such as filtering and Fourier transforms. Specialized units improve overall efficiency and performance of FPGA applications. So here we can see the input data stream and output data stream. In between we can see the interconnects where it includes DSP slice and arithmetic operations and accelerated tasks. Reconfiguration mechanisms. Static reconfiguration involves programming the FPGA once before operation. Dynamic reconfiguration allows parts of the FPGA to be reprogrammed during operation. Reconfiguration techniques enable adaptability for evolving system requirements. Fabrication technology and progression we can see in this. Early FPGAs are used relatively simple CMOS processes with limited logic density. Advances in fabrication technology have allowed for higher transistor density and lower power consumption. The progression has led to larger, faster, and more efficient, energy efficient FPGA devices. So here we can see in 1980s to 1990s at early FPGAs there is low logic density and larger transistors with higher power. Coming to 2000s, having advanced CMOS, increased density and smaller transistors. It improved the performance. Coming to 2010s, ultra low power, extreme density and tiny transistors. So, coming to the years, the transistor size is being reduced and the performance is increased and the energy is efficient with larger capacity. Architectural trends and innovations. Hierarchical interconnects improve routing efficiency at larger scales. The integration of hardened IP blocks and specialized units enhances versatility. Innovations focus on balancing flexibility, speed, and power efficiency. Power management strategies. Power consumption is a critical concern in FPGA design. Techniques such as power gating and dynamic voltage scaling are employed. Architectural improvements aim to reduce static and dynamic power usage. High performance FPGA architectures. High performance FPGAs incorporate multi gigabit transceivers for high speed communication. They utilize advanced interconnects networks like hierarchical and mesh architectures. These features enable applications in telecommunications, data centers, and scientific computing. FPGA scalability in and modular design. Modern FPGAs are designed with scalability in mind for larger and more complex systems. Modular architecture facilitate customization and reusability of components. Scalability supports systems ranging from small embedded devices to large data processing units. So here we can see the FPGA scalability. Small embedded device, which is the FPGA to the sensors, coming to the mid-size system, whereas the DDR memory and communication interface are in the form of FPGA, and coming to the larger data processing unit through the high speed interconnects. Here we can see the multiple DDR interface networks, which has the modular component of FPGAs. FPGA development tools and design flows. Design tools include hardware description languages, HDL like VHDL and Verilog. Synthesizers and placement and routing are key steps in FPGA development. Evolving tools support higher level design, abstraction, and automation. Challenges in FPGA architecture. Managing power consumption and heat dissipation remains a significant challenge, ensuring reliable configuration and avoiding hardware faults are critical concerns. Balancing flexibility, performance, and cost continues to drive architectural innovation. Future directions in FPGA architecture. Integration of AI and machine learning accelerators within FPGA architectures is emerging. Development of more energy efficient and adaptive interconnects is ongoing. Advances aim to further close the gap between FPGA performance and ASICs. So here we can see the future directions in FPGA where its performance is closer to ASICs. Coming to the conclusion, FPGA architectures continue to evolve to meet the needs of complex high-speed applications. Ongoing research aims to enhance reconfigurability, performance, and integration. Staying updated with architectural principles is vital for leveraging FPGA capabilities effectively. Thank you.